one which is based on minimizing mean square error which leads to basically LMS algorithm. There is another category, a very powerful category also, in some sense very powerful, not in all sense, that is called recursive least squares. So, we will be now marching towards recursive least squares approach. It is also called RLS abbreviation. So, most often I will call it RLS, call it as RLS rather than recursive least squares. To initiate this, to kind of introduce you to this topic. So, suppose we consider a random variable d and a set of random variables x1 dot 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 xp. They are spanning a space, all 0 bin random values say w. Okay. And I want to estimate d as a linear, best estimate as a linear combination of x1 to xp. Then you have seen that what will that be? That will be nothing but projection of d, orthogonal projection of d on the space w. We have the inner product there, inner product is a correlation. So, for the time being assume all, for this RLS business assume everything to be real, because complex will be a little more difficult. You can generalize also, whatever result we get for real, we will extend it to, we can easily extend it to complex case, but for the time being you assume that we are dealing with real valued random variables. So, they are we are given already the inner product in the space as the correlation between any two random variables. E of x y is the inner product between x and y. Okay. With that, keeping that inner product in mind, you know that if you orthogonally project d on the space w, what you get is that best linear combination of x1 to xp, because the error then is the one having minimum norm square, this minimum variance, and that error is orthogonal to each of the elements, that you all know. Okay. That is you want to find out PWD. PW is the projection operator corresponding to this W, D projected on that has some kind of Ci Xi. Okay. Maybe instead of P, you replace it to be, instead of P, use some other name Q. Okay. So, x1 to xq. So, this is what we do in a mean square estimation. How is this PWD? It is such that d minus this quantity, the error should be having minimum norm square, and obviously that will then be orthogonal to x1 to xq. That comes from the theory of orthogonal projection, right. So, there what we do there, we found out the error E was d minus this Ci Xi and we said that you take the variance of this error epsilon square, all are real. So, just E square is enough. Okay. This is a quadratic function of Ci and has to have a one unique minima, and which it is, because it is quadratic function also. So, you find out all the coefficients, those coefficients are obtained as what in terms of the autocorrelation values of the correlation between x1 to xq and the cross correlation between d with each of x1 to xq. That is, if you define x vector as x1 x2 dot 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 xq, then you define the matrix R as E x x transpose. Transpose is enough, Hermitian is not required because all are real, and say P vector as E x d. You understand? In the optimal filter case, we had the variable x n minus 1 up to x n minus q or whatever. Instead of that, I am considering a little more general case, just q independent random variables q1 to independent means q defined random variables x1 to xq, that is all. Okay. But treatment will be same. The optimal filter coefficient vector will be R inverse P, isn't it? How did you obtain that? You knew that this E is orthogonal to each of the vector, each of the elements x1 to xp. If you have this coefficient vector C as C1, C2 dot dot CQ, then this error E can be written as D minus this x vector transpose, this is all repetition, x vector transpose C, isn't it? X vector transpose C vector, this is the summation D minus, that is the error. And how to obtain C? We knew that this is an orthogonal projection. So, this error must be orthogonal to each of the components of x, each of the random variables. So, that means, if you take this E of x vector into E, is a scalar, x vector means x1 into E, x2 into E, dot 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 xq into each of the term will be 0, and that gives rise to E of x. You replace E by this expression x into D minus E of x, x transpose C. This is your R matrix, this is your P vector, and you get that C optimal as R inverse P. This slightly more general way of doing things than that filter case, in which case these variables are nothing but x n minus 1 dot 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 x n minus q here. I am just making it little general, but approach is same. It is orthogonal projection, the error has to be orthogonal to each of the components. So, you put the components in vector form, each correlation term here will be 0, from that you get this equation that C optimal is R inverse P, is not it? This was the one, this was the thing we started with that time. And then we said that look, R and P, these correlation values may not be available with me, or may be something that changes from time to time. So, in that case my algorithm should be adaptive, so that I do not have to supply the system with this information about R and P, because simply because I do not have that, also that changes from time to time. So, it should be made adaptive, so that from the data only it adjusts itself, so that actual R and P is they are learnt in some indirect way from the data. With that mission we started. So, we instead of computing this directly by R inverse P, we said that first we go for an iterative procedure called steepest descent. Okay, because what is the steepest descent procedure? This epsilon square is a quadratic function of all the weights. That quadratic function had one unique minima corresponding to the orthogonal projection. Okay, so you start with an arbitrary weight vector C and then go in the opposite direction of gradient, and that was bound to provided you choose the mu step size there correctly within its limit, it was bound to converge on exactly on the optimal point there in the steepest descent. But steepest descent needed the exact value of R and P in the gradient computation. Remember, exact value of R and P, but I said again in the beginning that R and P are not known to me, that is why I have to make things adaptive. Then from that steepest descent I took one step ahead, and there I brought in approximations that okay, R and P you replace by wild approximations. R is simply, see in this case x vector times x, instead of taking many such products and averaging, just one x vector with its transpose. P vector also just one x vector into D instead of taking many such products and averaging. So, I am introducing approximations there, and immediately I am paying a price. What price? That I can have convergence subject to proper choice of mu, but convergence is not exact convergence, it is only convergence in mean. So, it is not that filter weights will converge really on the optimal one, it will be dancing around the optimal one, the mean of that being the steady state, steady state as n tends to infinity, but of course, we really do not have to go for n equal to infinity. After sufficient runs, there is a steady state, and that time, so after 200, 300 iterations usually you find steady state, and that time weights this filter coefficients, each of the coefficients will fluctuate, but fluctuation will be around the optimal value. But at least convergence is taking place, but not absolute convergence, not convergence on mean, not convergence exactly, convergence only in mean. That is the price we pay, because I injected those approximations in the beginning. R and P were replaced by very wild estimate. So, number one was that we are not getting absolute convergence, we are only getting convergence in the mean. Secondly, even if you had not replaced R and P by those wild approximation, but you still carried out only steepest descent as an offline procedure using correct value of R and P, suppose you know that, even then that is a search technique. That is a search technique, you will be going opposite in the opposite direction of gradient, again move further, sometimes in a gradient is positive, so go in the opposite direction, go backward, sometimes gradient is negative, so go forward. So, backward forward movement, that will take sufficient number of turns, and then only you will converge, if at all converge, and then you are going into approximation. So, this actually LMS is nothing but searching in a steepest descent sense, but with some approximations. So, obviously, search means as such it will take time to find its optimal value, and then it is using approximation for R and P, which means to be a very approximate search. That is why it will take a lot more time to reach that convergence stage, and convergence also will be in mean. These are the two problems in LMS. And that rate of convergence, that depends on actually the data statistics, because R and P they are related, R and P they are required. R and P, if I mean I have not taught all this and I will not teach, just I can just give you this information that suppose the input autocorrelation matrix is such that the eigenvalues of that autocorrelation matrix there is a huge disparity. Suppose the autocorrelation matrix is positive definite, so all are positive real, it is always real because Hermitian, but suppose it is positive definite, so all are positive real, and the highest to lowest eigenvalue ratio is very high. In that case, it will take far more time to converge. On the other hand, if all eigenvalues are having similar value or same value, it takes less time. So, again convergence also depends a lot on input statistics. These are the problems in LMS. From here we go to another class of adaptive algorithm, where we will be looking for exact convergence. That approach will be free of, it will be basically, I mean, it will not be rejecting the statistical notion that expected value, mean, variance, but it will not be explicitly using E operator anywhere. And as a result, it will give rise to convergence exactly, no convergence in mean, it will give exact convergence, number one. And also, it will take far less iterations to converge there. Only thing, the only price that you of course pay, and because of which I mean, it has not been so widely used even today, is that it requires more computation, because you are trying to look for, you see, I mean, better result, more accurate result, faster result. So, naturally more computation, and if you are to look for VLSI implementation, not all forms of this RLS are really very good. Okay. So, LMS still I would say, I mean, when the RLS came up in middle of 80s, early 80s, we all thought that RLS will kill LMS, but LMS has survived. But again, RLS also is very good. Okay. So, let me go to this RLS thing now, recursive least squares. Here, this is the epsilon square. What is epsilon square? There is the E operator, variance of the error. This is directly the random variable. And this is a linear combination of those random variables. This is the error. Error is a random variable. You take the square of that, all real. So, the square of that expected value, this mean square, and this will be a quadratic function of Ci and all that. That is how we proceeded. Now, suppose what I am doing is this: I want to find out an estimate of these first. What will I do? I will take one value of d, one experiment, one observation, so one value of d, and similarly one value for x1, one value for x2, one value for x2. I observe all of them once, find out the error. Again, next time I observe another value of d, and again observe the corresponding values here, again find out the error. Constants do not change, Ci is the same. So, every time I find the error, I square the error and go on adding after sufficient number of times, 100 times, 150 times. If I average that, that will be a good estimate of epsilon square. But that average thing will depend on your choice of these coefficients, isn't it? Suppose I minimize that quantity with respect to these coefficients, that also will be a square function of quadratic function of this coefficient, because after all, squaring these terms, it will still be a quadratic function of. So, you minimize, you get a set of coefficients. Point is, if you take sufficiently large number of such observation samples, this epsilon square will be almost equal to this, and it will have a unique minima because of the nature of the mathematical nature of the function. It is a quadratic function of the weights. So, then the minima point will give rise to, or will be very close to the optimal one, at least intuitively so. We will expand on this, we will really show that it is indeed the case. Let me now make it more formal. Suppose I am observing d from time t equal to 0 onwards, n equal to 0 onwards. So, it becomes a time series. It gives rise to a sequence of observation. It becomes dn, d0, d1, d2, d3, d4, dot 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 up to nth index. Nth index is the current index. So, I have a sequence or a record of data d0 to dn. Similarly, I observe each of the random variables x1, 0, x1, 1, x1, 2, dot 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 x1 n. It gives rise to one sequence. Okay, sequence I put in a vector form. So, dn suppose is a vector. It is nothing but it will start at d0, go d1 dot 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 dn. Xin vector, and these vectors are purely column vectors. N indicates the current index. You start at, starting point could have been anything. I am starting at 0. So, then I form a summation epsilon n square. This epsilon n square is not this, there was no n here. I am defining this new notation. This will be what? first take the error at 0th index C I x I 0, this error square, then d 1 minus C I x I 1 square plus dot 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 plus d n then you should divide by the total number of terms. But I am not taking that, because if I minimize this is a quadratic function of the weights. This is a quadratic function. You see, you are squaring up, na? Coefficients are not changing. My point is I am using a set of coefficients C0, C1, C2 dot 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 and just combining those observations x1 to xq. So, at 0th index I got some data for x1 to xq, I combined them, took the error, numerical value of the error, square up. Take another case, at n equal to 1 I got some data for d, some data for the xi, x1, x2 dot 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 xq, again combine them with this, took the error, squaring up and going on adding. So, if I have sufficient large number of terms with that averaging in mind, then this will be a good approximation of epsilon square, is not it? But now this, suppose I have sufficient terms here, but you see each term has got square of this filter coefficients. So, it is a quadratic function of the weights, that we will see later also, it is a quadratic function of the filter weights. So, that means this will have a unique minima and this will give us, I mean, so if I differentiate it with respect to each coefficient and all equate to 0, you will get a unique minima. Okay. That minima will give rise to a set of coefficients. Those optimal coefficients, that is, if you define C as I already defined it, C q, and if you do this del C epsilon n square equal to 0, differentiating and equated to 0, you will get the optimal coefficients. My point is, you see, the optimal coefficients C I should be replaced by C I cap, cap is for the estimate, instead of writing opt here, I am putting a cap, because already there is a subscript I, so no point in putting a comma and another subscript opt. This is the optimal one. By how is obtained? By solving this equation. You are differentiating with respect to C I is equating to 0, you get a set of linear equation like we did in that optical filter case, winner filter case, you get a set of, but they I should now replace, instead of just this, as a function of n. You see, I have used here data up to n and I form this sum of square errors, square error, square error, square error, sum of square error, so many terms. The entire thing is differentiated with respect to C i's equated to 0, you get a set of solution, you get solution. Suppose I make it now epsilon n plus 1 square, get one more term to this. Again the entire thing is differentiated with respect to C i's equated to 0. You will not get this. Simple mathematics, you will not get this. This new expression has come, again overall minimization has to be done. So, that is why that will be then called C I cap n plus 1. In the recursive least square 6, you will be given C I cap n and the new data for d n and each of the variables.
Sir, one question. This epsilon n square, you have defined that every, d n minus C I x n, x I n, and then
Data up to n, yes. So,
just squaring it up and adding it up. Why don't you do that modulus of each term?
no, I have not, I will do that later. I will do, let me proceed, there is a plan by which I am proceeding. Okay, this is taking data up to n, taking data up to n. C I cap n. In the recursive least squares, please listen to me, you will be given previous, that is up to, the optimal filter coefficients up to nth index, that is using data up to nth index, whatever best you could get, this will be given to you, and the n plus 1th index data for d, that is d n plus 1, and for those variables x 1 n plus 1, x 2 n plus 1 dot 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 x q n plus 1 will be given to you. The new set of data will be given for the index n plus 1 and the previous estimate will be given. You will have to find out by simple equations in a recursive way the new set of weights C I cap n plus 1. That is the entire story. No approximation anywhere. You see, I have removed E operator, no business of E and all these things. That is playing a role in, because After all, the sum of square of errors, it will give rise to this epsilon square. After all, we will approximate to epsilon square and all that. But when I give this mathematical problem, there is no E operator anywhere. It is a numerical linear algebra problem. It is very interesting and far more trickier far more challenging than gradient directly that lattice on. We will see this.
But this is a direct extension of that. I mean,
What?
direct extension in the sense that once you take a lot and then average it, you will converge to the mean directly.
No, but before I converge, I have to have the equation na. I have to take this to Ci cap n to Ci cap n plus 1 to Ci cap n plus 2 dot dot dot, finally it will converge.
And you want a recursive.
I want to have this recursively. I want to have the, if you want to go on doing it every time by the first principle calculation, you will be finished.
But yes, that also we have just one term appended each time.
But summation over is not like lattice that one term will give a separate contribution. I will add to that. Not so easy. Not so easy. It's not. What he's trying to say is that thing that okay, if you add one extra term, its contribution can be computed separately and add to the previous estimate. It's not so easy. Not so easy. Overall minimization will lead to some Ci cap n plus 1 that will not be so easily related to Ci cap n. It's not so easy. I am looking for exact relations now, no question of any approximation anywhere. Okay, so we have understood our purpose. The basic purpose of recursive least squares is this. Or even if I Ci cap n, instead of Ci cap n, I may be interested in the projection itself, like the filter output. So, instead of just Ci cap n, I may be interested in combining these terms using the Ci cap n and get the projection. So, get projection using like this quantity. Suppose this I know, because Ci cap n I know, find out this quantity, find out, given this, find out. This also I may be interested in. Then instead of the coefficients, I may be more bothered about this. You can say the filter output or combiner output. Okay, you got the philosophy, no? But one thing you see, you can tell me so far that okay, you are getting one estimate, next time you had one data, again do overall minimization, you get Ci cap n plus 1, then Ci cap n plus 2, but where is it going to? It will always give you new and new estimate. My question is no, because obviously you understand that at least theoretically, if I take to infinity, you do not have to really go up to infinity, you take a sufficiently large number of n, 100, 150, that is fine, but otherwise theoretically this is equal to the correct epsilon square, no doubt about it, isn't it? So, if you take in this epsilon square infinite such terms, theoretically speaking, again that will be a quadratic function of the weights, and if you minimize that, whatever you get, that will minimize this also, is it so? And minimum that is unique, minimum of this is unique. So, that means those coefficients will indeed exactly converge on the optimal weights. I am not talking about I plus 1, what is I? Oh, sorry, it is n plus 1, thank you. Yeah. You understood this, the philosophy? Theoretically, if I take infinite number of such terms, then that is equal to this, with the averaging in mind. I will be basically taking up to say finite number of terms, divide by the number of terms and let the number of terms tend to infinity. That ratio will turn out to be for very large n epsilon square. If I minimize that with respect to the coefficients, then finally the coefficients will converge on those ones which minimize epsilon square, and that is optimal ones. But there is no expectation operator. I will take this square and minimize this quantity. So, that means, if I now find out a recursive relation for each I, if I recursively can find out Ci cap n, then Ci cap n plus 1, then Ci cap n plus 2 dot dot dot, then that will finally converge on the optimal value for Ci, exactly, not in mean and all that. And also intuitively you can see it will converge very fast, because no approximation, no search. I am not doing any search blindly and all that, isn't it? It should take much less time and also no approximation anywhere. That is why convergence is found to be faster. Okay, but computational burden for this is much more than LMS, and also structurally it will not be so nice as you have for LMS, for VLSI implementation. Okay, those are the things that we pay for. Okay. So, to get into this, let us now again come back to the corresponding vector space notions quickly. Yeah.
So that summation sign.
If there are some silly mistakes here, then you correct it yourself. Tell me please. Yeah. Where is the size?
Ci xi.
Yeah, here. This one.
Yeah, I from so xi will vary from
Each xi goes from xi0. Xi is a variable here, random variable, and these are the data samples. These are the data samples for each xi. This is summation. What is the confusion here? At n equal to 0, I found some real data for x1, x2. I call them x1 0. That is xi variable giving rise to, that is what I told you, na, they giving rise to a sequence or vector. The variable xi gave rise to, when I observe their numerical values, by observe trial after trial after trial after experiment after experiment, I got values, I put them in a vector form, which is also a sequence.
So what will the data space for xi plus 1?
My God. I varies from 1 to q, x1, x2, xq. These are fixed, x1, x2, xq. I took any arbitrary xi. I could be 1, I could be 2, I could be q. Any of them is changing from at n equal to 0, I got some numerical value. At n equal to 1, I got some numerical value. I put them in a vector form. So at n equal to 0, I find out the numerical value of the error. What is the error? Take the value I obtained from D, take the values I obtained from various xi's, combine them. That is, this quantity I evaluate at n equal to 0. I get this. This quantity I evaluate at n equal to 1. I get this. I am squaring and adding, that is a good estimate of the, which I am calling epsilon n square. For large n, that is a good estimate of this. Is it understood or Joseph, is it understood? Please understand, this is the basic. If you do not understand that, then the entire RLS thing will crash.
So is there any relation between n and I?
I corresponds to the filter coefficient. and
I is independent. I have got I, how many i's? x1, x2, xq. I am taking a general xi here. I am taking a general xi here. I could be 1, I could be 2, I could be q. Each of them I am observing at n equal to 0, finding out the value of the error. At n equal to 1, finding out the value of the error. Squaring of the error, adding, that is a good estimate of this quantity. That I am minimizing with respect to these coefficients. And if I have got sufficiently large number of data for each of these variables, so that the averaging for this is done over a large number of samples, then that epsilon n square will indeed turn out to be very close to epsilon square. So, if I minimize this, whatever optimal values I get, that will be the ones which minimize these optimal ones, isn't it? You understood this? This is basic. This is the basic thing in RLS. Is this clear to all? To him? So, now in order to do everything in a vector space framework, let us now define the corresponding vector space or rather inner product space. I am dealing with real valued data here, absolutely. So, suppose I consider R, actually it is called script R, it is for real, or N is a vector space of all n cross 1 vectors, and these vectors are actually column vectors. N cross 1 vector means really column vectors over R. That means each entry of the vectors is a real number. You understand that this is a vector space? How to add two column vectors? Sample is add, you get still a column vector of dimension same, it remains in Rn. There is a quickly Rn is a vector space that even I mean very trivially it is obvious. How? Consider any two vectors of length n, you add them, you still get a vector of length n closed under addition. Then a vector, I mean Rn has got a vector all 0. So, 0 vector is there, because if you add any other vector with that 0 vector, you get that original vector. With every vector there is a negative of that also, because to every element you change the sign. You get the negative of that, you add that 2, you get 0 vector. all that associativity, commutativity, everything is valid. Take any column vector, multiply by a scalar, real scalar, you get still a vector of length n, and all other properties are valid there. It is a vector space. It is a vector space of dimension n. How I showed that is an example. You can consider a trivial basis. For this, one is 1 0 0 0 0 0, then 0 1 0 0 0 0, then 0 0 1 0 0 0 0. How many you get? N such vectors. They are linearly dependent and they span the entire thing, because any n corresponding vector can be obtained as a linear combination of those trivial bases. That means, this is spanned by the trivial basis, but total number of vectors in the trivial basis is capital N. So, dimension is n. Once I know the dimension, finished, I do not care for the trivial basis. All this is repetition. This I took up as an example of vector space R n. Okay. Its dimension is n. Here I define inner product between any two vectors x and y as what? That is, if x is say x 0, sorry, x 1, x 2, x n, then the inner product is simply sample wise multiplication and addition, x I or maybe x k, not I, y k, k from 0 to, sorry, k from 1 to, starting it is 1 to n. Just sample wise multiply and add. This will satisfy all the properties of inner product. First, you can see x 1 plus x 2 comma y. Here also x 1 k plus x 2 k into y k, you can separate out, linearity is valid. X and y are y and x, in this case they are real, so they are same here also, x k, y k, x k, no change. C times x into y, c x k, c can go out, and x with itself means summation mod x square, all are real. So, x square means mod x square actually, because x is real. So, that is always real, non-negative and equal to 0 only if each x square k equal to 0, because everyone is x square. Each x square k 0 means x k 0, that means all the components are 0. So, it is a 0 vector, fine, it is an inner, this is the most standard inner product. Okay. But remember one thing, if this x corresponds to a random variable, that is though there is a random variable x and I am observing capital N number of some data, in capital N number of times I am observing it, and I am putting all the data in a vector form. I observe this random variable x once, get x 1, next time x 2, next time dot dot dot, next time x n, put them in a vector form. Same for y. Then this inner product x y, it is n times, if I write 1 by n, this is a good estimate of the correlation between x and y. Suppose you want to find out that, okay, you are giving me two random variables x and y, e x y, you want to find out. Okay, e x y you want to find out. X is a variable here, not vector. X is a random, that is why I am not putting any underscore. X is a random variable, y is a random variable. E x y you want to find out. A good estimate of that will be what? You observe x and y for various indices at n equal to 1, n equal to dot dot dot, n equal to capital N, multiply sample wise and add an average this quantity. So, just this inner product is nothing but capital N times, for large number of cases of course, it is a good estimate of capital N times the correlation. So, in fact, if you take this and divide by 1 by capital N, this will go, and this is a good estimate of the correlation. If it is x comma x, it will become capital N times good estimate of variance. Okay, please see this. Okay. And in any case, this E x y, if I now take this quantity as it is, and I am saying as though x is not just numerical data, it is a sequence. So, every time it is a sequence actually. Every time you observe, you get one value for this, one value for this, dot dot dot, one value for this. If you view it that way, this is another viewpoint. Similarly, one value for this, one value for this, one value for this. Next time you observe, this sequence changes, this sequence changes. In that case, inner product value will change from observation to observation. One observation means one set of value here, one set of value here, if you see it that way. in that case expected value of, but inner product is, this inner product is changing, data changes from case to case. One observation, one set of value, one set of value, one value of the inner product. Next set of next observation, one set of value, one set of value, another value of the inner product. So, it is random. So, expected value of that will be what? E x k y k. But E x y, if I call E x y as R x y, then this quantity, whether it is k equal to 0, k equal to 1, k equal to 2, this quantity will always be R x y. So, this is n times R x y. Okay. So, this inner product is such. So, if I divide by capital N, if it is 1 by n, this gives rise to R x y. So, this inner product is such that mean value of that inner product indeed gives, that is, if you really you bring in expectation operator, take the mean of that and mean value of that divided by 1 by n indeed gives the actual correlation. This kind of estimates are called, this from estimation theory, unbiased estimate. Forget this for the time being, let me tell you something about unbiased estimate. Suppose there is a parameter theta you are observing, you have to estimate theta. So, you are observing lot of data for theta, using that you are finding out some theta cap by some algorithm. Again next set of observation comes, so your theta cap value changes. Again another set of observation comes, observing some data, data set. Again theta cap comes, your algorithm working on the data set and give you something. So, your estimate itself is random, because that is dependent on the data set. But the theta cap is varying, but if the expected value, mean value of the theta cap turns out to be same as the original theta which is being estimated, then it is called unbiased estimate. It is very crucial in estimation theory, whether an estimate is unbiased or not. Sometimes theoretically you can find out that estimate is not unbiased, but there is a DC component added, which is also okay for us. DC can be subtracted, DC fixed, non-deterministic, deterministic quantity, non-random quantity added. That is, expected value of theta cap is not just theta, theta plus some c, where c is a non-random known constant. So, you just subtract out c, you can get your, at least from expected value of theta cap, you can get your theta. But sometimes that quantity is either unknown or even random, not random, unknown. After expectation it cannot be random. So, it is unknown, then there is a problem. Okay. These are something I told you from estimation theory. So, this is the inner product thing I have. So, using this notion, and I already told you what I do in recursive least squares, the sum of square thing, this I will be minimizing, right. This I will be minimizing. Now, you see how I write it. Suppose I have got a vector d n, and now I will be in this vector space R n plus 1, that is vectors of length n plus 1, starting from index 0 to current index n. So, length will be n plus 1, I am in this vector space over real field. So, I define d n vector as, in fact, I have already defined them. So, no point in rewriting. I take these definitions. So, these vectors belong to R n plus 1. Okay. So, suppose I now consider a space W, maybe W n I put, spanned by these column vectors, mind you, column vectors x 1 n, x 2 n, no longer random variables, no random is no expectation, no random, nothing now from now onwards. It is absolutely pure and simple linear algebra. But relation of course, the statistical relation was there, otherwise you can say that why are you doing this exercise. The fact that you will converge to the optimal one, there that stochastic thing comes and all that we have already elaborated. Okay. X q n. I am assuming these vectors to be linearly independent for the time being. That also has to be seen and verified. You will see that these vectors are not always linearly independent. All those things will come up, but for the time being assume they are linearly independent. Conditions required for them to be linearly independent, that will be satisfied, suppose, and W n is a space. and PWN is the orthogonal projection operator, ortho projection operator for Wn. Then my claim is whatever we are doing here is nothing but what we did, we found out this error and minimized this with respect to the coefficients and got them, got the optimal coefficients which are function of n. My claim is nothing but computing this as linear combination of these elements, that is computing this, that is I am doing orthogonal projection of Dn on the space spanned by this. I will have it verified. Now, only listen, Dn vector, suppose I project it orthogonally on this space spanned by this. So, that projection I define like this, notation only, which will be a linear combination of these. My claim is there you will get the same coefficients as you get by solving these equations, that is minimizing this with respect to these coefficients. That is easily seen also, that is this is my claim, you will get the same coefficients here. Obviously, because suppose I want to compute the projection, suppose I want to compute the projection, a projection of what? Dn on the space spanned by them. So, that means I want to find out or maybe I do it in another way. You are minimizing this sum, that time you are minimizing this sum, but can I not write it like this, that it is visible, no? D0 I am using the subscript n because coefficients after all will depend on the index n, because I am using data up to index n. If it is instead of n, it is n plus 1, n plus 2, new coefficients will come. Only for that I am using this notion. Suppose I consider this first, D0 minus summation of these terms C1 n times x1 0, C2 n, that is what you have here. This quantity is nothing but first, this reality is a vector, column vector minus matrix into column vector, which is totally column vector, column minus column, column vector. What is the first element of the column vector? This quantity only, isn't it? D0 minus, you are combining them, instead of Ci I am putting Cin here, because that is more correct to bring the dependence on n explicitly. Okay. So, C1 n times the data for x1, C1 n times the data for x2, dot Cq n times data for xq. This n only indicates that final coefficients which will be obtained by minimizing, I should make it dependent on n, because I am taking data up to n. If instead of n I have one more data, I will get new set of coefficients. So, that is why I should show the dependence on n explicitly. Then D1 okay, that is this quantity, isn't it? And dot Dn current index last quantity. So, you get a vector, first element is this, second element is this, dot, third element is, last element is this. If I take the norm square of the vector, square of first element this, square of second element, dot, square of last element added as per my inner product definition. So, minimization of thus means minimization of the norm square. And what is this quantity? I told you how to carry out matrix vector multiplication. C1 n times this column is x1 vector n, this column is x2 vector a, this column is xq n, and this column is dn. So, this error vector, if you call it en vector, is nothing but dn vector minus you can write this way Cin times the corresponding vectors. That is dn minus a linear combination of those x1 to xq. You find the error, that error vector norm square is this square sum of square errors. That you want to minimize means you are finding out the orthogonal projection, because you are minimizing norm square. Norm square in the new vector space Rn plus 1, but you are minimizing norm square. Are you getting me? This minimization of this is nothing but, this is very simple actually, this is nothing but this quantity, which is nothing but, that is this error, take each term of the error, square up, first term, second term, last term, square up and add. That is a, take the error vector, take the norm square of that. You are minimizing the norm square error with respect to the coefficients. So, you are minimizing the norm square of this with respect to the linear combinatorial coefficients. From orthogonal projection theory, this norm square, because that orthogonal projection theory was independent of the vector space, particular type of vector space, that is general. So, again that projection will exist, will be unique, norm, the minimum norm square solution will come up, which will correspond to the orthogonal projection, the error will, this error will be orthogonal to each of these terms. Okay. This error will be orthogonal to each of these terms. And what will that error be then? So, you understood that this is an orthogonal projection problem. Projecting dn on the space orthogonally, projecting orthogonally dn on the space Wn. So, the projection will be a best linear combination of these column vectors. Those are the coefficients. This resulting error vector norm square will be minimized because of these guys. Okay. So, what are these coefficients here? Let us find out. We know in the case of optimal filter R inverse P and all, but that entire business is out of the purview, no E operator anywhere and all that. But you can carry out a similar treatment. You are telling me En is orthogonal to, this vector, this matrix, you permit me to call Xn, capital Xn, fine. So, this equivalently I can also write as dn minus Cn. Cn is, I already defined earlier, Cn consists of those C1n, C2n dot Cqn. Those coefficients I put in a vector form. So, xn into Cn. This is Cn, this is your Cn, the intermediate, fine. This error is orthogonal to each of the fellows, fine. That means x transpose n E n, that should be 0. What is x transpose n? X n first column is this vector. When you make it transpose, this comes up here on top as row vector. What is x transpose n? First column, and next class please come with this preparation, otherwise very soon you will be totally lost actually in this topic. I am telling you, this far more difficult than whatever you studied so far mathematically, far more challenging, exciting and some difficult. And these things are used in not only the signal processing adaptive filter, most importantly you are learning something which is useful in many contexts today. See the generality of the things, I pick up things in this course which are used elsewhere also, this recursive least square techniques and all, okay. It is not that it is in the context of adaptive filter, so you do not take much into not that. Now, x transpose n means first row, first column, very simple, na? This is x1n, so this it becomes a row, x2 transpose n dot times En vector. And what is this x1 transpose En? What was our inner product? This inner product is what? this I can write with x here, y here, I can write x transpose y or y transpose x. Sample wise multiplication addition na, x transpose y, x1 into y1, x2 into y2 dot dot dot. The two vectors just one column, that is what is happening here. This fellow after transposition has become rho times En, that inner product has to be 0 because En is orthogonal directly, not in random sense and all that. En, because they are spanning the space, En is orthogonal to this guy. So, either En transpose this column or this column transpose En, both is 0. Then same for x2, same for xq. So, this is 0 vector directly, exactly, without any expectation of point anywhere, fine. But now En is this quantity, to substitute En is this quantity. So, now substitute xn dn vector, sorry, x transpose n dn vector, x transpose n, En means this quantity. So, dn vector minus Cn is 0, which means Cn is so that means I can write like this x transpose n x n into Cn as x transpose n dn, right. This quantity, if I divide this by 1 by n plus 1, I divide this also by 1 by n plus 1. What is this quantity? And this quantity is a matrix after all. X transpose n is a matrix, x n is a matrix, so the relative is a matrix. Just a scalar times every element divided by a scalar. So, entire thing. So, what is Cn? You can ignore this also, but I am putting it for a specific region. Okay. This 1 by n plus 1 and this will cancel, after all you see 1 by n plus 1 is not required here. So, Cn will be just inverse of this matrix times x transpose dn. Okay. Actually, when I use it later, I will not be bringing the 1 by n plus 1, they cancel. Two things are important. In the next class I will show this is not always invertible, but I am assuming it to be invertible. We will see when it is invertible. It is not always invertible. Those exact conditions have to be seen, but I am assuming that we are in a condition where this is invertible. Secondly, what is this quantity? X transpose x means what? Very quickly, first row is x1 transpose n, x2 transpose n, dot 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 xq transpose n, and here x1 n, x2 n, dot 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 xq n. First one will be x1 transpose with x1, norm square of the vector divided by n plus 1. For large n, it will be a good estimate of the autocorrelation variance of that random variable x1. Then x1 transpose x2, it will be a correlation between x1 and x2 for large n. So, this entire quantity for large n will approximately equal to R. This quantity will approximately equal to x transpose into D. So, you have got this not present, only dn. So, x1 transpose dn, correlation between x1 and D, x2 transpose dn, correlation between x2 and D. Okay, so, this will become P approximately, and you get R inverse P. Okay, so, this solution approaches the optimal solution for large n. That is all for today. Thank you. Please come prepared with all this next class.